Welcome to ECE 302. This is lecture 3.4 on expectation. I am Professor Stanley Chan. To start with, I want to tell you a story. Long time ago, in a galaxy far, far away, there are some kids on another planet took a midterm exam. And this is the score that they got. So we have student 1 through 75. And then this is a histogram summarizing their scores. And so a teacher came and the teacher looked at the scores and the teacher thought that the scores are just too low. And in order to avoid any complaints from the parents, the teacher decided to give 10 points to all the kids in the class. So the question that we want to ask will be the following. By looking at the histogram here, certainly we can calculate the average. In fact, this is something that we would do every day. And now if we add 10 points to everyone, what will happen to the average? Or using a technical term, we call it the mean. We can also ask, if we add 10 points to everyone, what will happen to the standard deviation? Furthermore, we can ask, if the letter grades are assigned based on the scores, and it will be based on the curved scores, meaning that I do not look at the absolute value of the scores, but I will look at the relative position of the student to the class. And so if the letter grades are assigned according to a curve, will this action of adding 10 points to everyone change the grades? I guess at this moment, many of you have already got the answer. Based on your experience, based on how you will calculate the data sets using software such as Excel. But what we want to do is to look at this extremely simple problem in a much more deeper sense. In a sense that we want to understand how do we calculate mean, standard deviation from not just a histogram, but from the probability mass function of a random variable. Furthermore, we want to understand these operations, adding points or multiplying the scores by a certain number, what will it change our mean? So this goes to the outline of today's lecture. We're going to understand the meaning of expectation. And now if you look at the outline here, we have two sections. In this lecture, we're going to look at part 1 of the discussion on expectation. And then in the next lecture, we're going to look at the properties of expectation. And afterwards, we will also study a generalization of the expectation to higher order moments and variance. So let us start by discussing the definition of expectation, and then we will draw the linkage from the expectation to the histograms and averages that we used to see in a dataset. The expectation of a random variable x is defined using the forward-looking formula. The notation of the expectation is given by E applied to a random variable x. On the right-hand side of this equation, we have a summation of a product between x and also the probability mass function, px. So how do we understand this equation? if you look at the equation down here, this equation that involves a product of x and px can be visualized as 1. It is the state that the random variable x takes. Now, here, remember that the small x is just one of the many possible states that the random variable x can take. And so when we are writing the summation over all the possible small x, then this small x refers to a state. And then here you have the probability mass function evaluated at this state. Okay, and so now when you multiply them together, you're really taking the weighted average of the state and also the chance of happening, and then you sum over all the possible states. So to help you visualize, let us look at this diagram. Suppose you have a histogram or you have a probability mass function that has this shape. You have 5 possible states, and then you have 5 different probability mass values, P1, P2, all the way to P5. The definition of expectation, according to the previous formula, it is the summation of all the possible x with x times px. So what is this x? The x will refer to one of these 5 states. What is px? Px refers to the height of the probability mass function. And so when you take this product of x times px, you're really literally multiplying this number with this number. And when you try to sum this pair of products up, then you are going through this list of possible states. So if I want to write it out explicitly, then I will have x1 times p of x1 plus x2 times p of x2 plus dot 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 plus x5 p of x5. So what is it? Well, you're just multiplying the state. This is your value, and then you multiply this p. P is sort of like the proportion of samples that will take this state. So for example, if p is 0.1, then you are saying that I'm going to multiply 10% of my samples with this value x1, and then you add with x2 multiplied with another number, maybe 0.2, and so on. So when you add them up, you are taking the weighted average of all these states. The weight will be the probability mass, and the states will define the values. So this is the formal definition of expectation, and it is actually not too different from our normal understanding of an average. Now, if you recall this histogram we just looked at before, which is the histogram of all the scores of the students, this histogram can tell you the mean, or it can tell you the average. How do you do that? Well, you put all the numbers into bins, and then you multiply the number of samples that takes that value with that value, xk, with pk. You multiply them together, you sum them up, that will give you the average. And so if you look at this empirical average, which is the average I can calculate from the histogram, it is more or less exactly the same as the probability mass function, which is the value x times this proportion, or what we call the percentage. We multiply them, and then we add them up. Now, if you do in this way, what do you have? Well, this is more or less just taking 1 over n. Here I'm using k, so you have n samples, n going from 1 to capital N, of all the possible samples that you have in your data set. Okay, so what is it? Well, let's say this is your data set that you have all these data samples. I put a superscript of 1, a superscript of 2 to denote these are the first sample, second sample, and so on. So this is the normal notion of average. You just add all these numbers up. You take you divide by the total number of samples. That will give you the average. Now, you can also try to group all these numbers into small bins. Each bin will have a center. For example, here is the cave bin, and then you put the numbers all into their closest bins. And then this is the histogram, and you can also calculate the average from this histogram. So there's a very, very minor difference between this is the calculation based on the summing all the samples divided by the total number of samples versus this histogram way of calculating the mean. The difference is that we are assuming that all these samples, when they live in the same bin, they can be well approximated by the average. Okay. Now, if this approximation is not correct, then you will suffer from a little bit of the approximation error. But overall speaking, this is a very, very good way of calculating the average. And you can see that why is that our expectation a very good capture of what we are doing in our practice. However, there's a problem here. The expectation is not exactly the same as average. Not because of the approximation that we are talking about, but because of a more fundamental issue. Recall this set of diagrams. Here we are throwing a dice, and we understand that it has 6 faces, and therefore it has a probability mass function that will be equal for all the 6 faces. If you do an experiment for only 100 times, this is the empirical histogram that you will get. This is the empirical histogram you will get when you throw the dice 1,000 times and 10,000 times. If you try to calculate the average from this finite example, okay, then you will be able to get an average somewhere here. If you have experiment like this, you may be able to get an average somewhere here or somewhere here until the moment that you have infinitely many training samples, then you will be able to get right in the middle of this uniform distribution. So what is the message here? The message here is that the expectation is computed from the probability mass function, which is a deterministic number that comes out from your random variable. Every random variable will have an expectation. The average, on the other hand, it is computed from the empirical histogram, and therefore, if you do the experiment today, you have this histogram, you will have a different average than another experiment you carry out tomorrow, because the histogram will become different, and therefore the mean will also become different. So expectation is not the same as average. Average itself is a random variable because you're taking the average of all these n random variables. Expectation is a deterministic number, is a number that comes out from the probability mass function. Let us work out a few examples to make the calculation a little bit more clearer so that we will know how to calculate the expectation. So here is a random variable x with PMF having 2 states, 0, 1, and 2, with probability mass functions defined as follows. We want to calculate the expectation. The expectation of this problem is you need to calculate the state. Let me remind you, expectation is the summation of all the possible states times the probability mass. And so here, what would be the state? You have state 0 with probability value of 1/4 plus state of 1, and then probability of 1/2, and then state of 2, probability of 1/4. So here it will get 0, that will give you 1/2, this will give you 1/2, and so you will have 1. Okay, and therefore you are getting the expectation of this random variable being 1. Now example 2 is the following. Suppose you flip an unfair coin where the probability of getting ahead is 3/4. Let x be the random variable such that x equals to 1 means getting ahead. Find expectation of x. So you have that probability x equals to 1 is 3/4. And since you are flipping a coin, there is only one more case, which is the complement of the first case. That will give you 1/4. And so the expectation of x is 0 times 1/4 plus 1 times 3/4. This is the state, this is the probability, state, and probability. Okay, here is the state, here is the probability. So you multiply them together, add them together, you get 3/4. Let's work on one more example. In this case, we consider a random variable x with a probability mass function given by this formula, where c is a constant which we need to find out. And furthermore, we want to find out the expectation of x. So how do we find out the c? Well, we know that the summation of all the possible probability mass has to give me 1. And then this k will go from 1 to infinity. Now, if I plug in this equation, then I have k going from 1 to infinity, c divided by 2 times 2 to the power k. This is just c times 1/2 plus 1/4 plus dot dot dot, and this can be simplified as c/2 of 1 plus 1/2 plus etc. And so you have c divided by 2 times 1/1 minus a half, and so this will give you 1. And so now 1 times c. Now if you equate this 1 with this c, then you will know that c equals to 1. Having found out this constant c, we can also calculate the expectation. So the expectation is the summation k going from 1 to infinity times k times p of k. And what is this? This is just the summation of k going from 1 to n to infinity, k times 1/2 to the power k. And this will give us what? This will give us 1/2 plus 2 times 1/2 to the power 2 plus 3 times 1/2 to the power 3, and so on. So this is the moment that you can apply one of our identities, which says that 1 plus r plus 1 plus 2r plus 3r squared plus dot dot dot, that will equal to 1/1 minus r squared. Okay, so you can plug the number in here, and then you can complete the calculation. Then you will be able to find the number by yourself. So I will leave this as an exercise for you, and I will encourage you to try it out. Here is another example. Consider a game, and then let us flip a coin 3 times. you will get the following 3 types of rewards. You will get $1 if there are 2 heads, $8 if there are 3 heads, and then you get 0 if there are 0 or 1 head. The cost to enter this game is $1.50. On average, what is the net gain? So this is a word problem. In other words, we need to translate this problem into equations, and then we will be able to solve the problem. So since you're flipping a coin 3 times, and you're counting the number of heads, let us ask what would be the probability mass function. Clearly, there will be how many states? You will have state 0, 1, 2, and 3, corresponding to 0 head, 1 head, 2 heads, and 3 heads. To get the 0 head, what is the probability? Well, you need to flip the coin 3 times. And so we know that if to get the coins, to get a 0 head, you must get tail, tail, and tail. To get 3 heads, you must have head, head, and head. Okay? Now, how about the other 2 cases? Well, to get 1, you need to have a head, tail, tail, or shuffle the order. So effectively, what you will see is that you will get a probability mass function of this shape. Here you have 1/8, here you have 3/8, 3/8, and then 1/8. This is the probability mass function of X. And then we are going to assign values to these events. So what I'm going to do is that I'm looking at if I get 2 heads, I will get $1. Okay, so I'm going to change this 2 to $1. If I get 3 heads, I will be able to get $8. So I will get $8 if I have 3 heads. Now, if I get 0 head or 1 head, I will get $0. And so what I can do is that I can add these 2 things up, okay, to turn it into something like this. Okay, so here I will have 4/8, and then what is the dollar sign I will have? I will have $0. Okay, so this is the probability mass function for this problem. The previous probability mass function is the probability mass function of getting the number of heads. That's not the same as what this problem asks. Now with this probability mass function, we can calculate the expectation. So the expectation of X would be $0 times 4/8 plus $1 times 3/8, and then plus $8 times 1/8. So that will give me 0 plus 3/8 plus 8/8, and that will be 11/8. Okay, and so what is the cost to enter the game is $1.50. This is equals to 12/8. Okay, and so the net gain is 11/8 minus 12/8, and so you will on average lose 1/8. So what does it mean? This example shows you that on average you are going to lose. It does not mean that if you enter the game once, you will lose. Because if you enter the game once, this is completely random, and so you will have a good chance of getting 3 heads. Who knows? Okay, but if you play the game long enough, meaning that you just keep playing the game, then on average, you will start to lose money. This is a typical strategy of a casino where the net gain could be slightly lower than 50%. They do not need to win all the time, but given enough customers, given long enough time, if the net gain is slightly less than 50%, then they will earn a profit. So I hope with all these calculations, you have seen how do we proceed to calculate the expectation given a probability mass function. Now, we also need to address one very important question, which is the difference between mean and average. Some people prefer to call the mean as the true mean and the average as the sample mean or the empirical mean. There is a substantial difference between the two. The true mean, as it is called, it is a statistical property of a random variable. It is a deterministic number. It is often unknown and is often the question of machine learning or estimation. Now, the sample mean or the empirical average is usually denoted by this notation, where you have a bar above the variable. This is a numerical value calculated from the data. So if you give me a data set, I will be able to return you this thing called the sample mean, which is the average of all the data points in the data set. This number itself is a random variable because today I have this data set, tomorrow I have another data set. They are coming from the same random variable, but they're just two different realizations of the same random variable. Because they're different, the sample mean from here will be different from the sample mean I calculated there. Okay, and therefore itself is a random variable. This sample mean has uncertainty, and this uncertainty certainly it will reduce as I use more and more samples. And so we will study this problem later in our course, that we will see how the sample mean can be used to estimate the true mean. So if you're trying to understand what I'm talking about here, you need to understand that the true mean is a top-down approach. You start with a random variable, and then you calculate the expectation. Okay? Now, here it is a different thing. The sample mean is that you start with a data set, and you go back, and then you ask about what is the empirical average. These two, they are not the same. Okay? This number will converge to the expectation as the number of samples goes to infinity. So we will study this link later on in our course. At this moment, you just need to know that everything we have talked about so far on expectation, they are coming from the expectation, which is coming from the probability mass function. So does expectation always exist? Does mean always exist? The answer is no. Let me show you one example, and you will see why expectation does not always exist. Here is a random variable x with a probability mass function given by this equation. You can do a simple calculation and show that the summation of all these values of k will give you a sum of 1. Now, what is interesting is that if you try to calculate the expectation of this random variable, which is k times p of k, where k will go from 1 to infinity, this is the same as the summation k going from 1 to infinity of k times 6 divided by pi square k square. Now clearly this k and this square will be cancelled, and so you will have k equals to 1 to infinity, 6 divided by pi square of k. Okay? Now, one thing to notice is that 1 plus 1 over 2 plus 1 over 3 and so on, this infinite series is actually going to infinity. Okay, and therefore, if you plug in this result into here, you can see that the expectation is going to infinity, and therefore the expectation of the random variable x does not exist. It is a legitimate random variable, this x. However, the probability, the expectation does not exist. For an expectation to exist, the random variable has to be absolutely summable. What it means is that if you put the absolute value on x, and if you take the summation, that has to be a finite number. Okay, so not all random variables will have a expectation. Only those absolutely summable random variables will have expectation. So this concludes our discussion of the first part on expectation. When we come back next time, we're going to study more properties of expectation, and then we will learn variance, standard deviation, and other moments. I welcome you to post any question on Piazza, and we also welcome you to send us emails if you have any question. Thank you very much.